Okay, so we have two folks that have participated now in the 5 block challenge, and this was put forth by Pete Ferguson, and he's in Windsor, Ontario, Canada, and he actually made the little blocks and suggested the idea for video material, and I thought it was pretty cool. So, and just to refresh your memory, what this is about is when you're grinding the chuck of your surface grinder, you evaluate the results based on the 5-block test, right? Where you distribute 5 blocks on the magnet, and then you grind them all to the same quote unquote same thickness, and then you measure them very carefully and see where the thickness varies, and it gives you an idea of how the machine's actually grinding, and it's a pretty definitive test as to how things are. Now, so we have two folks that did the grinding here. These are Pete's, and this is our other competitor, I guess you would call it, and that's Alex Kern, and he's in Allentown, Pennsylvania. And I've met both of these guys in person, and they're both cool cats, and so I thought we'd do a little measuring on these and see what we have. So now I've asked, and I'm not going to go through all the details here, I'm just going to collect the information. I give each one what I call a data sheet here that where they fill in, and they tell what kind of grinder it is, what the table type is, the abrasive details, coolant, no coolant, how they dress the wheel, depth of cut, roughing, depth of cut finishing, and any other comments or anything, speeds and feeds, that kind of stuff. So in general, I'm just kind of, it's an opportunity to collect a little bit of information on these results, right? Okay. So now the idea here is also we'll measure these, and whoever's are better, quote unquote, will be the reigning champion, and then the other blocks will go out to the next volunteer that wants to try this. Okay. So out of this measuring pass here, there'll be some blocks available for somebody to take up on and grind and throw their hat in the ring. So pay attention. Okay, so we're all set up over here. Get the amplifier, Brown and Sharp amplifier, and the Brown and Sharp gauge head. So what we'll do first, these have been sitting on the surface plate for a while, and so they should be equilibrated nicely. We're just going to give them a quick clean, and this is a lint-free clean room wipe, so we're just going to give them a little rub and give them a quick cleaning, both sides, then evaporate a little bit. And we'll just run them through on low resolution to start with and see what we have. And these are Pete's blocks here. We're going to do those first since he turned his in first. So I kind of nominally said it before, and it looks like it's pretty good still. The big head in there. Make a little adjustment. Okay, looks pretty tasty. Check it a couple times. Now at this resolution, the heat from my hand's not a big deal, but if we start getting into the fussy ones, which would be to the right, then that will make a big difference. So, all right, so we're calibrating 0 on 1. Let's see what we got for number 2. That looks pretty good. 3. Okay, so we're plus 3/10 on that one. Double check. Yeah, +3. All right, let me write that down. That was number 3, +3. Okay. And then 4, let's see what 4 is. 4 is +1. Let's do each one a couple of times here. Yeah, +1, +1. And then number 5 is, looks like +1 too. I'm going to call that +1. It's a little more, but okay. So let's see. Number 1 was 0, and number 2 was also. And let's verify our 0 again here. Yeah, looks pretty good. Looks like there's some variation depending on what side of it. Oh yeah, oh, look at that. So these parts, it's tapered a little bit is what it looks like. Yeah, okay. Looks like our 0 is still okay. All right. Okay. All right. All right, let's check the other ones and go from there. All right, so I zeroed up on the number 1 block of Alex's. I'm going to move this. This is not conducive to writing here. Okay. Yeah. All right, the same. Number 3. 0. 4. Oh yeah, these look so far so good. These are all well within a tenth. And this one's got a little spot that didn't quite clean up. Yeah, okay, so we're going to have to change resolution on these and go to a higher resolution. So this is this particular scale is 3 thousandths total range. Each tick is 1/10. So we're going to bump up to the red scale, which is the lower scale, which is going to be a total range of 1,000ths, and each division is 50 millionths. Okay, so let's do that. All right, let me get 0 to number 1 again. Okay, we're going to kick it up a notch. And usually there's an index shift when we do that. So I got to, oops. And it just gets, this is where this electronic zeroing is really nice. Oh, actually got it pretty good. Okay. So I'm going to probably start having to worry about heat here. You know what? Let's just do it. So I got my chopstick heat shields. Let's see if I can do this. Alright, so I'm happy with that. There's number 2. Oh, look at the right scale there, dumbbell. I was looking at the wrong scale. One thing you got to pay attention to there. Okay, I got a good 0. Alright, so that's 20. What do I see there? Okay, that's plus something. Okay, that's plus something. I'm interpolating between the lines, so that's plus something. I'm just going to make a mark that it's plus something. Number 2. Don't know exactly what. Let's see, 2, that's 3. Do these in order. Sorry if my head's getting in the way, but I got to eliminate parallax there. That looks pretty damn good there. Yeah, that's a sweetheart. Okay. Oh boy. These are pretty tasty here. Dang. Okay, let's do that one again. These are looking pretty sweet. Let's check number 1 again. Number 0 is good. All right, so this thing's been driving me a little bit bonkers here. We're in the 10 millionths resolution mode, and there's enough variation in the part across the size of the part that it I just breathed on it there, that it's causing trouble with the measurements. So I don't know if you can see it, but I put some tick marks on it at 90-degree increments, and I fished around, and well, we'll just move it around and you guys can see. So we get a little bit of variation depending on where we measure the part. So it brings basically uncertainty into the measurement, right? So you know, what should we call it, right? Well, I think the only thing that makes sense is to back off on the resolution a little bit, and then where we get a little bit more I don't know, consistency, I suppose. So I can measure them all in the same place, but that doesn't really doesn't give us a definitive answer, I guess is what I'm trying to get to here. So anyway, when we're in the 50 millionths resolution, then you know, the thing stabilizes considerably. So we're below 50 millionths and above 10 millionths, something like that. So in that region. So anyway, the deviation as best that I can determine on these Alex's blocks here is in the 10 to 30 millionths range, somewhere in there, right? And that's about all I'm prepared to kind of say, which is considerably better. That's probably what was the big number on Pete's? +3. That's 10 times better than the first set of blocks. The maximum was 3/10 on that, and we're going to say 30 millionths on these. So that would be the spread. So these are 10 times better by my estimation. Okay, and you know, like I said, I got a little bit frustrated there for a bit, and I switched gauge heads. I tried a couple of different things, and so I'm fairly confident that there's enough variation in the part that it's just causing measurement inconsistencies. So if I measure a gauge block, for example, and I drug some out here that were close in size. You know, these are lapped, very, very smooth and very, very flat and very accurate. The measurement consistency jumps up nicely. So anyway, so here we are, and if somebody else wants to step up and regrind these 5 here, shoot me an email, please. Email address is at the beginning of the video, and shoot me an email address with your mailing address, and I'll send these out. First come, first served, and you guys can you try your hand at this. It's kind of fun. So, all right, next thing up. All right, so we got a couple of additions to the library here. Let's take a look at them in order here. And these came from England. I had these shipped from England, which is you know, you can do that these days, right? You can look at book inventories all over the world, which is, if you're a book lover like me, pretty fantastic. Now, these are from Caxton Press, and the Caxton, yeah, is a publisher. And yeah, I have a few other Caxton titles, so I didn't have these. These are 1950s vintage, I believe. Yeah. First edition, 1950, and the pictures kind of jive with that, which is kind of neat. So this is a 2-volume series, tool room practice, and then I have another one here, grinding, lapping, and polishing. But I've tagged a few things that are of interest to look at, and so let's check it out here. See what we got. Okay, so this is pretty cool. It's the first one here. So one, I'm familiar with the Hilger-Watts company. They make surveying instruments and metrology tools and whatnot. And I did not know that they made a protractor like this, okay, a bevel protractor, and they call it a microptic bevel protractor. So, which is pretty cool. And so now I got, well, you and you guys too, something else to look for on eBay, right? Now here's a pretty wacky looking device. It's called a sinometer. Never seen anything like this before, but it's got some some arms and some other things, and it's pretty wacky tobacco there. So and some little fine adjusts and whatnot. So it looks like it's possible that what they're doing is they're setting it off of a sine bar, and then they get, so they zero this, and then they can measure something and determine the difference from the reference angle. That's how I interpret that, okay? Which is kind of neat. And then this one I liked because it's got this cute little sine bar in there, and that's just a kind of a neat little size, and they're grinding something in there that looks kind of cute. Okay, and let's see what else we got here. Oh, and these are some more Hilger-Watts stuff. These are clinometers, and these are actually pretty neat for setting angles really quickly, and they're actually pretty accurate. So like drill press tables, you know, angle fixtures in a machine, because you can set a zero reference even though that it's not level. And then you can, and they're good to, I don't know, well, some of them are good to fractions of arc seconds, so depending on which model you get, which is kind of neat. Okay, and then the last one in this particular book, oh yeah, this is pretty neat. Never seen one of these before. This is a, I can't read it upside down, it's a senior, as in senior aged. It's a graduating machine. It's for cutting graduations on dials. So it's got some slides that move in various axes, and dividing attachment, and I'm sure it's a row tab too on top of that. So never seen one of those. Pretty neat. You can see the flaking from the decorative scraping stuff on there. Pretty cool. All right, let's check out the next one. All right, so this is volume 2 here from the Caxton books. Let's see what we got here. Oh, okay. This is what was interesting on this page here. So here, what they've done is they've made a master square reference using dial indicators that have a spread. So it has a little shoe down at the bottom, and this is kind of nice because once again it quantifies some angular offset, and that's something that, you know, if you have basically one good flat surface there and you mount a couple of indicators, almost anybody can create that. That's, that could be made out of an angle plate or something like that, an import angle plate with a couple of indicators, and you could get a pretty dang accurate square there, okay? And as everybody knows, squares are self-proving by reversing them, so you can kind of calibrate it. It's self-calibrating, which is another kind of neat thing. So, okay, so what else we got here? Oh, yeah, okay. This is pretty cool. So if you've ever had to measure the pitch diameter of internal threads, okay, you'll share my frustration, because unless you have, lots of thread gauges, and typically that's what you do, is you just buy the dang thread gauge and or the plug gauge, and then you can inspect the pitch diameter. But here's kind of a universal way of doing it here, and what they're doing is they have an adjustable parallel, and then they're using some balls that fit into the V's of the threads, and then there's some math involved, but you can measure here over the parallel and determine a pitch diameter based on the ball, etc. Now it looks like it's a little tricky to set up and get a reliable reading, but never tried that myself, but it looks like it might be worth a go. You probably have to grease these up and stick them in there so they kind of stayed, and then very carefully put that in there. So anyway, just a different kind of way to inspect pitch diameter of internal threads. Okay, this is the last one here. This is the grinding, lapping, and polishing. And this is volume 1. I think there's a volume 2 out there. I'm going to go poke around and see if I can find it. Let's see what we got in here. And this is, you know, same vintage, 1950. What do I have pegged here? Oh, okay. I'm always, you know, this is a great little project for somebody that's, you know, getting into tool making and whatnot, is to make a, you know, a balancing stand for whatever you want, right? And this one's interesting in that it's using precision rods here as the ways. So if you think about it, a round rod rolling at 90 degrees on a round rod, that's a pretty small contact patch. So it's probably very low friction. And then it's got leveling screws here so you can kind of trim it out and level it. The trick is to get those dead parallel with one another, which isn't, you know, super hard, but it's one of the tricks. And then, oh yeah, some of these are just cool imagery here. It's a gigantic roll that they're grinding here, some monster roll for something, I don't know, looks kind of large. 15-foot diameter, that says, so that's kind of neat. And then what else we got here? Oh yeah, this is another one that I thought was cool. So, you know, there's a class of work, big, heavy stuff, and this is a roll for a steel mill, I think, okay? And there's the typical drive notches you see in that. But if you look here, they're just running in the journals here on a steady rest. They don't have this between centers or anything like that. And here you can just barely see it. There's a driving dog here that's just rotating this thing, and the grinding head is grinding on that, okay? Now if you think about it, the grinding forces are very low compared to the mass of this roll. So on big honking heavy stuff, the machining forces are actually low in comparison to the weight or the mass of the part that you're working on. So there's a kind of the scaling thing that goes on when you get into some of the really big stuff. Obviously you got to, you know, hold it down and hold on to it, but you don't have, you know, the relationship between cutting force and part mass is a lot different with this kind of stuff. So anyway, I thought that was kind of neat to see that actually in practice there. So okay, so Caxton Press, some pretty cool little books. Okay, so this is this No-Bur type countersink that you guys saw me use the other day, and this thing is really cool, and it's kind of special. And guys that have thought about tool making and making their own tools and things like that, this would give you a method for actually making a countersink pretty much of any size that you want. Okay, so here's the blade. Okay, and you see the blade is just parallel, right? Okay, and it's got a straight little, you know, hook grind in it like that. Okay, and the troublesome part of countersinks is how they're relieved, right? Okay, well the way this works, and my friend Gordon Long turned me on to these things, and it's just very cleverly done. Okay, it has a little tapered wedge in here, and when you want to regrind this thing, what you do is you take out the little tapered wedge, you put this back in, okay, and then it's got this other little screw here which you can use to advance the blade in that direction, right? Okay, well let's see, let's put this back in, let's see if we can do this and kind of make a meaningful demonstration out of it. All right, well, I think maybe I need to do that. Oh, I probably have to put a little shim in there or something like that to clamp it. But when this is up against that shoulder without the tapered wedge in it, this is just a cone. Okay, it's just a cone. So you put it in your whirligig at an angle, and you grind a cone on that. Okay, and you know, to get a little bit more exposed, you can push that forward, right, and then you can grind that off, right, and it's just parallel. Okay, but to get the relief, okay, which is the tricky part, what they've done is they said, oh well, let's just do this. Let's just add this tapered piece in here. Okay, and now what that does is that tips that a teeny bit, okay, all right. It tips it like that, in that direction, okay, and gives you a relief. It's just super dog simple and really clever, right? So this is the using position, and then this is the grinding position here. So it's just sweet, okay? And you can see that, now this is probably the hardest piece to make right here, is to make this little wedge, okay? But even that is not that hard, right? I mean, you can put that on a magnet and grind it at a little angle, no problem, right? And this is all this straight lathe and mill work here. So if you wanted to make a countersink, say you wanted to make a 3-inch countersink, you had a big fat 3-inch hole that you wanted to do, you know, you could build one of these pretty easily. And that's just a piece of tool steel. You can probably snap off a piece of a parting blade or something like that, and you know, off you go. Let's see, let's seat that up in there. Okay, and lock that down, and that wedges up against that. And now you can see that that's scooted out. Okay, and now this is higher than that, and off you go. Anyway, just a kind of a neat design of a sharpenable countersink, so you can touch that blade up kind of anytime you want. So I thought you guys would like that, because I certainly did. Okay, so I think we've got the kind of the ultimate solution for our crate in a box problem. So this was actually well, the first person was a viewer that actually sent in a sketch of how to put the ends and the tops and the sides together without having any joinery. Okay, so they're just cut rectangles, and then having them interlock so that that they fit together nicely. Okay, and it's pretty simple. It's pretty good. So we're going to put one together, and we're going to give it a try and see how it goes. So now it's a little bit tricky to kind of get started here, right? That's the you know, I was playing around with this earlier, so it's like, okay. So you just need to needs to fit in between, like so. And the viewer that sent this in, his handle is Klaufman, and actually, you know what? I'm gonna back this up, because this is what seems to help get it put together initially. So you can kind of push things up, and you can see that it's all interlocking, right? These can't cave in this way, these can't cave in this way, and these can't cave in this way. So, you know, it's probably good enough just to plop in the box just like this and let her rip, right? But we're gonna go one better. I picked up a couple of different kinds of tape here, and this is this Gorilla duct tape, and then this is the filament packing tape. So the reason I chose these two here were because, you know, you can buy a small roll of this, okay? So, you know, in the interest of thinking of the end user, right? The empathy for the end user, right? You send them the box, or several boxes, and a roll of tape, and they're basically ready to go at that point, okay? They don't have to go out and buy anything, they don't have to order anything, they don't have to do anything weird, right? And, you know, they kind of got everything that they need. So this is my other part of my setup here. Just to kind of keep things kind of tight while we tape it up. And so let's tape it up, and then we're going to do our chuck test. All right, so let's get some tack welds on this, I guess you'd call it, right? And this stuff has like super califragilistic stickum on it, which is one of the things that makes it really nice. And it's not super expensive. It's not put it this way, it's better than that gaffer's tape that I was playing around with before, from an adhesion standpoint on a surface like this, which is kind of not optimal not optimal for tapes, right? And this is a good width too, by the way. I made that one too long, but we're not gonna worry about it. Okay, so let me finish taping this up and then we'll go from there. Okay, so we're taped up. No glue, no nails, no weirdness, right? And no particular fancy tools, okay? So the reason for kind of pre-assembling it on the bench like this is now it's a box, right? Okay, and I can put it in the real one now, like so, okay, without any trouble. And then the lid goes on. But ideally, what we would do is we would pack our parachute first, right? Put whatever we're going to put in there, and then slip it in here, and then go from there. We'll do that. Now, I think what I would do, since I got some tape left, is I would put a girth tape around this, and probably one in each direction should be fine. So I'm going to go ahead and do that, and then we'll load some stuff in here. And I'm just gonna hit the center line here like so, okay, and just go all the way around like that. Okay. Until I get one little overlap like so. Okay. Then we'll put our stuff in and we'll go once around that way, and Bob's your uncle. Alright, so we got our block of death here. And for those of you that were wondering, I had a black fingernail, and that's how I got it. The load shifted in this box and it drove me into the table and pinched my finger, and that's how I got a black fingernail that I've been wearing for a couple of months. Okay, so I'm going to tape these. Let's just do it proper here. And this is this tape. It's cheap and easy. I'm not driving nails. I'm not spooging glue all over the place and doing that. Okay. In that region. Girth around it right in the middle. And the ultimate insecurity. Now I don't want to squash my finger again, so gotta be a little bit careful. Like that. You hear that rolling around in there? That's the thing that'll hurt you. Oh boy. Well, it's already performing pretty good here, so okay, let's box it up. All right, and then we're just going to use the crappy Joe McGee tape here. We'll pretend like we're doing a good job and put a couple of layers on there, like so. The same on the bottom. Okay, I think we're ready for a chuck test. Knock knock. Special delivery. Fancy machine tool parts. And then just threw it over the back fence into the yard. See that again. So this is what James Green sees every week. Hello. looks pretty bulletproof to me. Look at that. I mean, we've crunched the cardboard against the edges and it's cut it, but other than that, it's pretty awesome. Okay, let's open her up. So, you know, and a lot of people commented and kind of stated the obvious. You would never pack anything in a box like this loose without some restraint inside the thing, okay? So, okay. I ripped the tape. That's pretty surprising. Let's open this thing up. Actually, try not to cut the tape there, Mr. Wizard. Part of our test, right? Okay. All right. Well, this is why you test things, right? So you can learn. And so it ripped that seam, and it popped the girth tape, which was interesting. Oh, it popped a couple of girth tapes. You know what? Actually, that might have been me cutting that one. That might have been Mr. Bozo, because that's a really clean cut there. It's not a rip like that. But it's broken over here on this side too. All right, so it opens up, and the box is beat to crap internally. You know, like I said, you know, you would restrain this, right? You would strap this down or put some foam or newspaper or cardboard around this so that it didn't shift. And that's really the, you know, part of the learning here, right? Is if you restrain the thing internally inside the box, you're going to be generally fine, okay? But this is for, you know, some person that doesn't pack things. They work in a you know, antique store, and they never ship anything, right? Machine tool wise, right? That's heavy and pointy and sharp and all that, and so they put it in a box and wrap it with newspaper, put it with packing peanuts, and you know, and expect it to get there in one piece. So I think we've tested this to death. I'm pretty happy with it, and you know, maybe an improvement is the filament tape, I don't know. You know, a couple more girth tapes certainly wouldn't hurt. Tape is pretty easy to add. All the woodworkers out there, you already know how to build a box. I'm not going to tell you how to build a box. This is for people that you know, don't quite know what to do with shipping something like that. Okay. Anyway, I hope you like the testing on that, and we'll see what happens with this. Maybe we'll do something with this idea.